Hello everyone from Math 2000, Linear Algebra. It's Professor Wenson here again with a video on your Zybooks section 9.2. It's titled Norms and Distances. Alright, so you saw in section 9.1, this introduction to inner products and an inner product space, right, which is just a vector space for which a function, these operations called inner products, are defined. And when a proper inner product is defined on a vector space, then we can get into the concept here of norms and distances. Now, norms are really just magnitudes, lengths, right? If you think back to Euclidean vector spaces, Rn, right, R2, R3, etc. The norm of a vector would be its length if the inner product was the dot product, and the distance between two vectors you're going to see is just the distance between the ends of the vectors when drawn in standard position, or starting from the same initial point. We'll get into all that here in a minute. All right. So for inner product spaces, norms and distances are generalizations of length and distance in Euclidean vector spaces, as I was just saying, and can be calculated and interpreted for any two vectors in any given inner product space. Norms and distance satisfy several properties similar to those of the dot product and magnitude, right, length in Euclidean vector spaces. They give an example here. The statistical process of finding a least squares approximation for a data set is built on the concepts of norms and distance. Right, so you have the objectives here, what's going to be covered. So the first thing to be covered in this section is called the Cauchy-Schwarz inequality. Cauchy-Schwarz inequality, a very important inequality in mathematics. So I highly recommend that's why it's got its own heading here. I feel like it should have its own section, but that's just me. So there are several theorems in this section rely on a relationship between inner products, and this relationship is called the Cauchy-Schwarz inequality. Alright, the Cauchy-Schwarz inequality is proved using the axioms for inner products along with the discriminant of a quadratic equation, which you may remember. I'm not going to read the proof. I'll let you read the proof, but here it is. Any two vectors, u and v, in an inner product space V satisfy this inequality, and this will always be true on some inner product space. The inner product of u with v squared will always be less than or equal to the inner product of u with itself multiplied by the inner product of v with itself. And again, this is true for any pair of vectors in an inner product space and any inner product, right? As long as you have an operation on these vectors from a vector space that satisfy, remember those four axioms, those four properties of an inner product. Right? You had the symmetric property, additivity in the first slot, homogeneity in the first slot, and that positive definiteness, right? If all four of those are satisfied, then this inequality will hold. So again, I'll let you read the proof and see if hopefully you can make some sense out of it. Alright, I'm not going to read to you. I suggest that you do not read example 921. If you see at the bottom here, earlier it said feedback sent. I sent some feedback to Zybooks about this, because the inequality they're having you show here, or the inequality they're supposedly showing is true, is not true. This is a false statement that this is less than or equal to this for all functions that are continuous over the interval from -3 to 3. You go ahead and maybe you can figure it out. All right, I'll leave that to you. But I was reading through this and realized they made a mistake here. So don't read example 921, or again, if you do read it, see if you can figure out why this is wrong. Maybe send them feedback yourself. Maybe the more they'll get, the faster they'll actually change it. All right, so I'm going to jump into the next thing. So I was reading through the rest of this. It all looks pretty good. All right. So here they're showing you how you could use this Cauchy-Schwarz inequality, right? This statement up here, to prove other statements about vectors, and prove that certain inequalities are true in certain vector spaces. So in this example, this activity, they're asking you to basically fill in the steps, right? What's the reasoning? And you've seen activities like this in other sections, right, where they run through a proof and you have to fill in the reasons for each line. So you see, match each property with each step to prove that u1 plus u2 plus u3, this quantity squared, is always less than or equal to 3 times the quantity u1 squared plus u2 squared plus u3 squared. And this is for any vector u in R3. So this is saying that for any vector in R3, the sum of the 3 components then squared will always be less than or equal to 3 times the sum of the squares of the components. All right, you see they're even giving you a little hint here, and you can use say vector u has components u1, u2, and u3, and vector v has components 1, 1, 1. Let's see. Now first they're defining the inner product here, right? So it's just the dot product, right? So they're defining the inner product of u and v to be the dot product, right? u1 times v1 plus u2 times v2 plus u3 times v3, the product of the components added up. So they're just defining an inner product in step A. And then given that definition, they actually go and say, okay, well, if I define v to be 1, 1, 1, then the inner product of v with itself would be 1 plus 1 plus 1, or 3. So this is just simply I guess put the number 3 there. I don't know why that's a reason for this. It should have had like application of the inner product or something on v. Same thing here. If u is defined to be this any vector from R3 and v is 1, 1, 1, then the inner product, dot product in this case, of u with v would be u1 plus u2 plus u3. So I guess I'll just put this in step C, the u1 plus u2 plus u3. And again, if u is defined to be this u1, u2, u3 vector, the way the inner product is defined, the inner product of u with itself would be u1 squared plus u2 squared plus u3 squared. So that's for part D. Whatever, it goes there. Alright, and then finally, this is what the Cauchy-Schwarz inequality implies then. See this left side? u1 plus u2 plus u3, that quantity squared, that's the inner product of u with v squared. and this is less than or equal to 3 is the inner product of v with v times u1 squared plus u2 squared plus u3 squared is the inner product of u with u. So this statement is an example of the Cauchy-Schwarz inequality, where the inner product is the dot product, and u is vector u1, u2, u3, and v is vector 1, 1, 1. Okay. All right. And I'm sure we'll get into more examples of that later. Or maybe you have an exercise. Let me actually go down and see if there's an exercise that I'll do some of. Yeah, so there's Cauchy-Schwarz norms. Yeah, it doesn't really look like they're having you use the Cauchy-Schwarz inequality all that often here. Well, I know I put up another video. I know I made another video in the past where I did more examples. So maybe you can watch that. And I'm hoping that helps understand the Cauchy-Schwarz inequality a little more. It's a little more important than they're I feel it's more important than they're letting it out here. All right. So now let's get into the the heart of the section, I guess. The title of the section is Norms and Distances. This is about norms in an inner product space. Alright, so the norm on an inner product space V is an operation that assigns a real number. Now, remember when we talked, this has been a while, but when we talked about the magnitude of a vector in Euclidean space, or the length of a vector in Euclidean space, you use this notation. Looked like a double absolute value symbol around a vector. Well, now this is going to be called the norm of a vector. Right. And the norm of a vector is, again, a real number for every vector in the vector space. Right. An inner product space has a natural norm. Right. So we're going to define the norm of a vector to be the following: the square root of the inner product of that vector with itself. Okay, so here's the definition of the natural norm for an inner product space. I'll just say the norm. All right. So the norm of a vector is defined here to be the square root of the inner product of the vector with itself. Keep that in mind. All right. The norm of a vector in a general inner product space is analogous, right, similar to the magnitude or the length of a vector in R2 or R3, right, Euclidean space, as I've mentioned. And here's another word you've seen before in Euclidean space. We've talked about unit vectors before. A unit vector is a vector, u or whatever you want to call it, that they're using u here for unit, such that the norm of u, or the magnitude of u, or the length of u, is 1 unit. All right. And all norms, all right, whether it be this natural norm, and we're going to be using the natural norm very, very often. This is how I'll define the norm in most cases. But any norm that you set up, right, for vectors in a vector space has to satisfy the following 3 properties. Okay, so properties of norms. So any 2 vectors u and v in an inner product space and a scalar or constant c, or a real number, satisfy the following properties. And really, well, these first 2 properties of positivity and homogeneity come from the fact that you have an inner product here. Right? If you define if we're defining the norm to be the square root of the inner product of a vector with itself. And if you recall from earlier, right, positive definiteness, the inner product of a vector with itself will be non-negative. Right, will be greater than or equal to 0. So then this square root, this norm, will also be greater than or equal to 0. Right. So norms should always end up, when you take the norm of a vector, it should never be negative. Again, this homogeneity deal comes from the homogeneity in both slots, right? I know there's homogeneity in the first slot, but you also have symmetry, so there'd be homogeneity in the second slot as well. If I did the inner product of c times v with c times v, well, you could take both c's out, and then the square root of c squared is the absolute value of c. So you see this norm of cv is the absolute value of c times the norm of v for any constant r, for any constant in the reals. And again, this second property just follows from the homogeneity property of an inner product. And finally, the triangle inequality. And this, again, hopefully is pretty straightforward. Think about it again as length. If you add to, the length of the sum of two vectors is less than or equal to the sum of the lengths of each vector individually. All right, now they draw up a little picture of this later, and they prove this using the Cauchy-Schwarz inequality. Right, and again, I'll let you read the proofs. Right. So the magnitude or the norm of the sum of two vectors will always be less than or equal to the sum of the norms of each vector. Okay. Right, and then we get into some other kinds of norms. All right, some other kinds of norms. Remember this up here. We're going to use this most often. Right? This is the natural norm to be defined on some inner product space. Right, saying the norm of a vector is the square root of the inner product of that vector with itself. But there are some other functions that satisfy these three properties as well, and they show you some of these here. So these are called the p-norms. All right, the p-norms. So for every these are now the p-norms. These different kinds of norms are just for Euclidean space, right? Just for Rn. So let's say v is a vector from Rn. The p-norm is defined as this norm with a subscript of p. So the same norm notation, but with a subscript of p. And it's pretty similar. Like when you talk about, I'll write this stuff out. But the p-norm of a vector in Euclidean space, it's the pth root, right? So if this was the 3 norm, you'd be taking the cube root. If it was the 4 norm, you'd be taking a 4th root. It's the pth root of the sum of the p powers of all the absolute values of the components. So you just make all the components positive, make all the components of v positive, raise them all to the p power and add them up, and then you're taking the pth root of that sum. This is called the p-norm on Euclidean space. And these p-norms do satisfy, and again, I'm not going to go into proving this, we're not going to worry about that right now. They do satisfy these three properties. You'll always end up with a non-negative norm when you take the p-norm. There's the homogeneity property where it holds. The triangle inequality holds for these norms. Alright, so they give you examples here. Alright, so I'm going to go with some paper and write some of these out. Alright, show you step by step these p-norms. So again, the p-norm on Rn, right, on Euclidean space, again, is this. The norm of some vector sub p, right, the p-norm. One more time, it's the pth root the pth root of, the absolute value of the first component to the pth power plus the absolute value of the second component to the pth power plus all the way to the absolute value of the nth component, right? It's from Rn to the pth power. Right? And I'll talk about the special case when p is 2, right? And we'll get into that in a second. All right, so for example, say vector v here is -1, 4, 2. Right, and this belongs to R3. Right, this is a vector from R3. Right. I'm going to show you some of these p norms. Now, I guess you could call a 1 norm just the sum of the component. Just make all the components positive, but that's not interesting. Right. Let's go for p equals 2. Let's do the 2 norm. So that would be this. Okay. Now you'll see in a second, I'm going to show you that usually with the 2 norm, you don't write the 2, and I'll show you why. But this would be the square root of, just again make all the components positive and raise them to the second power. So that's just like this 1 squared plus 4 squared plus 2 squared. So the p norm is the square root of 1 plus 16 is 17 plus 4 is 21. Right? So yeah, this is called the 2 norm of this vector, on R3. Now, a little note about 2 norms. If the inner product, so say if the inner product of 2 vectors is just the dot product, right, remember where you just multiply the corresponding components and add them up, then that natural norm, remember that definition I read out, I only read it out loud earlier, but remember this natural norm, the norm of v is the square root of the inner product of v with itself. Well, this would be exactly the same as the 2 norm, right? Because think about it, this norm of v here then, right? So if the inner product defined on R3 is the dot product, and v was this vector -1, 4, 2, then this would be the square root of -1 squared, which is 1, plus 4 times 4, which would be, again, I'm just multiplying the components by themselves, would be 16, plus, and then 2 times 2, 4, and I get the exact same thing. I get the square root of 21, which is the same as the 2 norm. Alright, like the 2 norm I just found up here. Right, so very often, sorry about the crunch on this, it's at the edge of the paper, I apologize, but so if the inner product that is defined on your Euclidean space is the dot product, then this 2 norm is simply the natural norm, right? The way it was defined earlier as the square root of the inner product of the vector with itself. So very often you'll see the 2 norm written without the 2. Right? So if you see a norm written without the 2, it's assumed to be the square root. It's assumed to be this natural norm. Okay? Alright, so just one point about the 2 norm. Alright, well, let's keep going. So that was an example of the 2 norm on R3. Let's take this same vector and do the 3 norm. Alright, now the 3 norm won't be equal to this square root of the dot product with itself, the inner product with itself. Only the 2 norm is special like that. So I'd have this norm of v with a subscript of 3, right, the 3 norm. Again, it's just the cube root, right, the cube root. And I just make all the components of v positive and cube them. So 1 cubed plus 4 cubed plus 2 cubed. Right. So this would be the cube root of 1, plus 64 is 65, plus 8 would be 73. Right? The cube root of 73, and there's the p norm. Alright, then I'll just do one more example here, and then I'm going to go to a calculator and I'm going to show you what happens as we raise the value of p higher and higher. Alright, what if we let p approach infinity? What would happen? Alright, so how about p equals 4? Let's take a look at an example of a 4 norm. Alright, so we have the norm of v with a subscript of 4 here. So again, this is a 4th root of 1 to the 4th plus 4 to the 4th plus 2 to the 4th, and this is actually one of the examples in the Zybooks page. This ends up being the 4th root of 273. Okay. And again, this can continue on forever. Right. So what I'm going to do now is let's think about what happens. Right, here's back here. Here's the formula, right? Again for the p norm. What happens as p approaches infinity? You just let the value of p get larger and larger and larger. Well, you take the 100th root of all the 100th powers of the positive components, add up the, make all the components positive, add up the 100th powers. You take the 1000th root, of make all the components positive to the 1000th power, add them up. The millionth, the billionth, the Googleth, the Graham's number, right? If you want to look up Graham's number, that's really, 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 really large. Anyway. What happens? Well, what happens is the component with the largest magnitude, right, the component with the largest value, because you're raising to higher and higher powers, will end up dwarfing the rest of them. So let's say V1 was the largest, had the largest absolute value. So you raise this to 1,000, a million, a billion, a Googleplex, or whatever. All right, make that larger and larger. Well, this will then eventually end up being so big that the other smaller components are negligible, right? Because you're going to infinity, you do this forever. These are negligible, and then basically this value is approaching this. The pth root of the absolute value of v1 to the pth. This will just be the absolute value of v1. So what you're going to see here is this, and this is called the infinity norm. All right, the infinity norm. The norm of v, with a subscript of the infinity symbol. And yeah, what you end up with is just whatever that largest absolute value of any of the components is. All right, you just end up with the maximum value, whatever the largest value of any of the absolute values of the components are. So the absolute value of v1, the absolute value of v2, the absolute value of v3, and so on, up to the absolute value of vn. Right, whatever the largest number of those is, this is what this will approach as p goes to infinity. So I'm going to show you this on a calculator. Right, so for this example, it would just be 4, wouldn't it? Right, the largest absolute value of any of these components is 4. You got 1, 4, and 2. Just be 4. So for this example, the infinity norm of v would just be the maximum value of 1, 4, and 2, which would just be 4. All right. And let me show you. Again, let me show you that when I do the 2 norm, the 3 norm, the 4 norm, the 5 norm, these values have a limit. They will approach 4. All right, so I'm going to pull my calculator up. So here was the 2 norm, right? The 2 norm was the square root of 1 squared plus 4 squared plus 2 squared, right? So the square root of 21, the 2 norm, which is your standard norm, your natural norm, was 4.58. All right, now I'm just going to second entry this. And change these to, you know what, actually I'll make this into a function. Let's do this. Y equals the square root of 1 to the x plus 4 to the x plus 2 to the x, and then just change the value of x. Alright, so then I go to my table setup. I like to change my table setup so that I have the independent variable on ask, right? And then go to my table and I can enter values. So you see 2, right? This is the 2 norm, 4.5826. 3, the 3 norm. That's the cube root of 73, right? The cube root of 73 is about 8.544. Oh, you know what? Nope. That's the square root. I typed square root. It should be cube root. I apologize. So let me change this again. My bad. Math. Let's put in the xth root. The xth root of 1 to the x. Yeah, this would be the x norm or the p norm plus 4 to the x. My apologies. 4 to the x plus 2 to the x. All right, this should be better. This should be better. So go back to my table. All right, so 2 norm. That's again the square root of 21. And I was like, yeah, that's. Remember, I said these should be approaching the infinity norm of 4, and I was like, ooh, 8. That's not approaching 4. All right. The 3 norm. This is the cube root. The cube root of 73 is 4.1793. Okay, and then let me enter 4. This should, and look, see, this is the 4th root of 273, the 4 norm, 4.0648. And let me put in 10. See, 4 point. Look at these values. See how they're approaching. Put in 100. It's basically so close to 4 that it just says it's 4. All right, this is really close to 4 already at the 10th root of all the 10th powers. The 100th root of all the. Now again, it's not actually 4. It's just so close to 4 that the calculator is like, hey, 4. All right. So you see, as the value of p approaches infinity, we get this, this infinity norm where all these p norms are approaching. Okay. All right. So then they have you, finding some p norms. So here's a vector from R2. I'll leave this one to you. All right, a vector from R2. Again, the 2 norm is just like the natural norm, right? If your inner product is the dot product, right, it would be the square root of the dot product of this vector with itself. Then you have your 3 norm, which involves a cube root, and then the infinity norm is easier than the other, all of them, right? And it's what's the largest absolute value among any of the components. Very, very easy stuff. All right, so let me do another example. Right. So here we're given an inner product on. Now this is the vector space. It's a non-Euclidean vector space, right? It's that vector space of all the continuous functions on the interval from -1 to 3. And this is that integration inner product that you saw in section 9.1. So the inner product of any two functions from this space is the definite integral from -1 to 3 of their product with respect to x. So let's find a norm and and then they're asking, is f a unit vector? Is the norm of f 1? So I'll write this out as well. Okay, so here's where we're given the inner product, right, on this vector space, and given a function, and we're asked to find the norm of this function, right? This function is a vector here, right? So I mean, it doesn't really make a lot of sense to say what's the length of a function. So we'll call it norm, right, or magnitude if you want to. All right. So now notice they have not defined the norm in any way. So if they don't define a specific norm for you, they didn't say find some weird definition of a norm, we're going to be using that natural definition of a norm. So remember, the norm of a function or the norm of a vector, the natural norm is the square root of the inner product of that vector, or in this case this function, with itself. All right, so we're going to use this definition a lot because this is a very natural definition, natural way to define a norm, and this satisfies all those properties. It's positive, it's non-negative all the time. It's got the homogeneity property, and it's also satisfying the triangle inequality. And you can check that if you want, but I'm not going to do that. We're just going to find this norm. So first I would like to find, off to the side here, what's the norm? What's the inner product of f, with itself? So this would just be the integral from -1 to 3 of f times f, or f of x squared dx. All right, so what does this look like? All right, so this would be the definite integral from -1 to 3 of, when I square this function, I'll have, sine squared of pi x divided by, and then square root of 2 squared is just 2. Right? And then, with respect to x. All right, so get your calculus hats on. All right. Now I'll do this a couple ways. I'll show you how to do this by hand here, and then with the calculator. This shouldn't be too terribly difficult. The sine squared of pi x. If you don't like dealing with some number times x, you can make a substitution if you want. Say let u equal pi times x, and then du, the differential would be pi times dx, right? And so dx would be 1 over pi du. And I can make these replacements and also change the limits. So the dx becomes 1 over pi, and I also have a denominator of 2 here. So I'd have 1 over 2 pi. I can pull that out. And then the integral, and I'll change the limits too, right? The lower limit originally was x equals -1. Putting that in here, the lower limit for u will be x equals negative pi. And putting 3 in for x in this substitution, we get u equals 3 pi, so the upper limit is now 3 pi. And then I have sine squared of u. Right, u is the pi x, and then du. Again, I replace dx with 1 over pi du. Okay. Now you might recall that you can't really do this right off the bat here. This sine squared, you're going to have to use a reduction formula. So this is 1 over 2 pi integral from negative pi to 3 pi. And sine squared, if you recall using the cosine of a difference formula, this is 1/2. And you remember cosine of 2u, right, hopefully this rings a bell, right? The cosine of 2u, you could write as cosine squared u minus sine squared u, or 1 minus 2 sine squared u, right? And then solving for sine squared u, this would be half of 1 plus the cosine of 2u. All right, and then we got du. All right. And I pull the half out, so we have 1 over 4 pi. And then I'll do the antiderivative of this, right, times, now I'm actually doing the integral. This is with respect to u, so we have u here, and then, plus half of the sine of 2u, right? And then the only reason I got the half there is because of the 2u, right? Imagine, you got to use the chain rule. If you were, if I differentiate this with respect to u, it's going to be 1 plus cosine 2u. And we're going from negative pi to 3 pi. And this is real nice here because, the sine of any multiple of pi, which I'll have in either one of these when I plug the upper end and lower end, is 0. So really this just ends up being 3 pi minus negative pi, or 4 pi. This ends up being 1. This ends up being 1. Alright, so lots of stuff there. Now you could have also done this, right? If your integration skills have been waning, on the calculator TI 8384, you can enter a definite integral right away, hit the math button, scroll down till you see fn int. Now on the newer ones it'll actually have you just enter all the stuff. The older ones you got to enter like the function, the expression, then the variable, and separated by commas, then the lower limit, then the upper limit. But I'll just, I got one of the nicer ones where you can just enter things as they look. So -1 to 3 of, and then in parentheses, the sine of pi x divided by the square root of 2, and then all of that squared, right, with respect to x. 1. See? So you can have the calculator do a definite integral if you wish. So anyway, back to the problem at hand. Sorry about a bit of a tangent there, or a sine. So this inner product, the inner product of this function with itself is 1. So now the norm of this function, the norm of f, is the square root of this inner product with itself, which is just the square root of 1, which is 1. So after all that, the norm of that function in this inner product space is 1. And since this is the case, this means that f, that function, this sine of pi x over the square root of 2, is considered a unit vector in this space. Right? It has a norm of 1. Right? And again, you can read all this here. Now, you see, they kind of just jump to the fact that it's 1, because you can use a calculator if you want. Okay. All right, and then here's some other examples. I'll just do one more of these, because then we got to get to distances, and we'll see distances are just more norms. All right. So this first one, I'll leave this one to you. Let's look at number 2. All right, so we're given that, remember the Frobenius inner product from section 9.1? It's basically just the dot product for matrices. You multiply, the corresponding element, you multiply corresponding entries in matrices and then add them up. So consider the Frobenius inner product on the set of the vector space of 2 by 2 matrices with real entries. And they give us a matrix A here, and they ask us, what is the norm of A? Right. So again, saying length would be weird here, because you're like, what is the length of a matrix? That really doesn't make any sense to say that. So you could say magnitude or norm, all right, and it would make a little more sense. All right. So I'll do this on paper as well. All right, so we have, I'll keep the calculator up. So, the inner product of two matrices here, say matrix A and B or whatever they are, is that Frobenius. I'll just write Frobenius. And this is the definition of their inner product. And this is on, that vector space of 2 by 2 matrices. And they give us a matrix, which is a vector here. Right? So this matrix they're giving us is this 2 by 2 with entries 1 divided by the square root of 6, 0, -2 divided by the square root of 6, and also 1 divided by the square root of 6 again. And they want us to find the norm of this vector, right? The norm of this matrix. So again, they didn't define a norm, right? And if they don't give a specific definition for a norm, just use that natural definition. Right? The norm of a vector, or in this case, a matrix, is defined naturally to be the square root of the inner product of that matrix with itself. Okay. So I'm just going to find, and off to the side here, what is this inner product of A with itself? All right, remember, this is just the Frobenius inner product, meaning I take the first row, first column entry and multiply it by, of A, and multiply it by, again, the first row, first column entry of A. So this will be, 1 over root 6 times 1 over root 6, which will just be 1/6 plus, then 0 times 0, plus -2 over the square root of 6 multiplied by itself, so positive 4 over 6, which is, I'll just put 4/6. You could put 2/3, but I'm gonna leave it over 6 so I can add stuff with a common denominator. And then finally plus, 1 over root 6 times 1 over root 6 again would be 1/6. Adding these up, and oh man, look at this. Get 6 over 6, which is 1 again. This is not always going to happen. I just happened to pick two examples where the inner product of a vector with itself was 1. This does not always happen. All right. So the norm of A then is the square root of 1, which is 1. So the norm of A is 1, and that means that this matrix in this vector space under this inner product is a unit vector. So A is a unit vector in R 2 by 2 under the Frobenius inner product. I have to specify the inner product as well because the way the norm is defined involves the inner product. All right. So again, I didn't mean for that to happen. I just it's another unit vector. Again, not every vector is a unit vector. Right? Just because the last two examples I showed you, I think maybe number 1 here won't be a unit vector. You'll see the norm of this polynomial here is probably not going to be 1. All right, and then you're asked to do this, 5 times here. Now you've seen the Euclidean norm. Whenever the word Euclidean comes up, you're talking about Euclidean inner product, Euclidean norm, Euclidean distance just means you're involving the dot product. Just means you're involving the dot product. So when they say what's the norm of v, the Euclidean norm, that'd be the square root of the dot product of this vector with itself. All right. So the dot product of this vector, now they're telling you 16 squared is 256, 30 squared is 900. Add them up, that'd be 1156. So yeah, this should be the. Now they ask you to round anything at all? No. Now maybe this ends up being a nice number. Let's see. I might have to. So square. What's the square root of 1156? Yeah, 34. It is very nice. So this Euclidean norm would be, 34. The magnitude of this vector, the length of this vector. Okay. Yeah. So if they ever say the word Euclidean, right, that just means the dot product is the inner product. The dot product is involved. All right. Then your next levels, and they'll probably have different vectors in different vector spaces. So again, find the Frobenius norm. That's exactly what I did a second ago. All right. This just means the inner product is the Frobenius inner product. Third level. Remember in section 9.1, remember that weighted Euclidean inner product? So with the weights 1 and 2, that just means you take 1 times the 7 squared plus 2 times 6 squared when you're doing this weighted Euclidean inner product. Right. And then the square root of that, of course, right? It's the square root of the inner product of the vector with itself. Again, if you don't remember what this is, go back to section 9.1. Talk about weighted Euclidean inner products. Remember the integration inner product? That was this one here, but with a different interval here, right, from 0 to 1 instead of -1 to 3. And find the norm of this polynomial. And then here, the weighted integration norm. Now, they didn't really mention weighted, but they're telling you, they're defining it for you here. All right. So the weight is 4x. So w of x here is 4x. And the inner product is defined this way. The inner product of any vector, any function with itself, is going to be that function squared, times this weight function, 4x. And you're, so find the norm of f in this case. Basically find this and then take the square root for this function f and this function w. Okay. So now, that was all about norms. Now that doesn't go away, right, for the rest of this section. On distance, what's the distance between two vectors in an inner product space? So just as norms are a generalization of length or size or magnitude, the distance between two vectors can be generalized for all inner product spaces. So the distance between two vectors, u and v, denoted by this symbol here, d, and then in parentheses you have u comma v, is just a norm. The distance between vectors u and v is defined to be the norm of the vector u minus v, which, if we use our natural norm definition, would be the square root of the inner product of u minus v with itself. All right, so if you already know how to find norms, you'll know how to find distances between two vectors. Okay, and then another definition here, a metric space. A metric space is an inner product space along with a distance function, like this. And all distance functions satisfy the four properties below. And again, these basically come from the fact that we're taking a norm. You know, the distance between any two vectors, because it's defined as a norm, will be greater than or equal to 0. The distance between two vectors is 0 if those vectors are the same, you know, or when those vectors are the same. Which is clear, hopefully, that you understand that if u and v are the same, you'll be just taking the norm of the 0 vector. Which, you know, if you take the inner product of the 0 vector with itself, that should be 0, right, by properties of inner products. Obvious symmetry, right? The norm of u minus v should be the same as the norm of v minus u. And, you know, because you had that triangle inequality for norms, you also have the triangle inequality for distances. All right, the distance between u and v should be less than or equal to the distance between u and w plus the distance between w and v. All right, so some other vector w is thrown in there. Again, I'll let you read over the proofs. And they have a little, you know, a picture here. If you were in Euclidean space, you know, R2, R3, talking about the distance between two vectors, you could think about it this way. You know, if you drew a vector v, and then starting from the same initial point, drew a vector w, the distance between those two vectors would just be, you know, the length of the vector between their ends, the arrowheads. Right, that's the norm of v minus w, the distance between v and w. So a way to think about it in Euclidean space. But you can also, again, generalize this to any inner product space. All right, so I'll just do one example here because, again, it's just finding a norm, but first you have to subtract two vectors. So they go over some examples here. So I'll go over the example. I'll let you read these examples and go over to one of the activities. Alright, so here, what about... I've already done an integration product and a Frobenius. I'll do number 2. I'll do number 2 here. Okay, so again here we have you know, that integration inner product, not weighted, on the, you know, vector space of continuous functions over the interval from -1 to 1. And we're given two functions from this space. You know, f is 4x squared plus 7, g is x squared minus 6x. And we're asked to find, you know, the distance between these two functions. All right, so remember this distance. Right, the distance between, you know, say, functions f and g here is defined this way. Unless they define it in some other way, but they're not going to here. Right? There are some other versions of distance that will also satisfy the properties of a distance function. But for right now, we're just thinking about it as this norm. It's the norm of f minus g, or g minus f. Right? You saw earlier the symmetry, they would be the same. And again, they didn't define a norm in any special way, so we can use the natural norm. The norm of f minus g be the square root of the inner product of f minus g with itself. Right. Okay, so if I want this distance, I'm, you know, doing this calculation here. Right, so again, I like to, you know, before I take the square root, well, let's see, what is f minus g of x? Well, that's just 4x squared plus 7 minus the quantity x squared minus 6x. So I'd have to distribute the negative. We have 4x squared minus x squared would be 3x squared. No x minus negative 6x would be plus 6x. And then 7 minus 0 would be 7. All right, so there's f minus g. And let me take this inner product of f minus g with itself. And this would be the integral from -1 to 1 of f minus g times f minus g, right? So of 3x squared plus 6x plus 7 squared. And then, with respect to x. All right, it looks like in the activity, they're having you type it as a decimal rounded to 1 decimal place. It's, number, point number. So what I'm going to do is just put this in my calculator, but with the square root as well. All right, so the distance then, all right, so the distance between these two functions, these two vectors, would be the square root of this inner product of f minus g with itself. Now, you could, it's not terribly difficult, but it would just take a while. And you could square this polynomial, get some ln degree 4 polynomial, and then integrate. It wouldn't be terribly difficult to find this integral, and then take the square root of that. But like I said, they just want us to round it, this distance, to 1 decimal place. So I'll pull the calculator back up again. Let's clear all this stuff. Now I'm going to do the square root of the integral, right? Math, and then down to number 9, going from -1 to 1 of the quantity 3x squared plus 6x plus 7, that quantity squared, and then dx, right, with respect to x. All right, so it's approximately 12.4. About 12.4. Right. Now, what does this mean? Okay. Well, really nothing yet. You could say the distance between these two functions is 12.4. Really, you're going to use these distances as more of a relative comparison. If the distance between f and g was 12.4, and then say the distance between this function f and some other function h, say these. Now I'm not going to tell you what h is. I'm just saying some other function out there h. Say their distance was 7.2 or something, which is smaller, right? Smaller than 12.4. All this would mean is that f is closer to h than to g, meaning that f has more similarity to h than it does to g. That's how these distance functions are usually used, as a relative comparison. So yeah, and the closer to 0 the distance gets, that means the two functions are closer and closer to being like one another. Right? They're closer to being the same, having the same structure, the same properties, whatever. Right? But for right now, we're just calculating distance. Right? 12.4. That's how we're asked to enter that here. There. Right. Okay. Wonderful. All right, and then you have your challenge activity. Again, I'll leave these to you. Here are two vectors from R2. And again, whenever they say Euclidean or weighted Euclidean, right? You're getting some version of this is when they say straight up just Euclidean. That means your inner product is the dot product. Right? So here you would take what is m minus n, then take the dot product of m minus n with itself, and then the square root of that. And there's your distance. Right? So pretty straightforward. Level 2, Frobenius, right? So you do the Frobenius inner product. First you find a minus b, right? You're doing distance between a and b to find a minus b. Then what's the Frobenius inner product of a minus b with itself? And then the square root of that, right, for your distance. Level 3. Now the weights here, so you take u minus v. Then you're not doing the dot product, you're doing 3 times the first components plus 1 times the second components and products, and then adding those up. So it's a weighted Euclidean. So it's like the dot product, but with a coefficient of 3 on the first components and a coefficient of 1 on the second. So you take u minus v, do this weighted Euclidean inner product of u minus v with itself, then the square root of that. Right. Integration, I kind of just did an example like this already just a second ago. And then a weighted integration product where this w of x shows up here, and this function in this case is 16x, right? So just make sure you're popping it. So you take f minus g, whatever that is, and then you have f minus g times f minus g, and then times 16x, take that integral, and the square root of that. Right? You get your distance, the distance between these two functions, f and g, under this inner product. Right? And that's it. So again, a lot going on there, but it really all involves finding inner products. You still have to know how, except for those p norms, right? Again, there are some other types of norms, other types of distances, but for the most part, when you want the norm of a vector, you're taking the square root of the inner product of that vector with itself. When you want the distance between two vectors, you're just taking the norm of the difference between those vectors, u minus v. And then of course you have the Cauchy-Schwarz inequality that I would recommend you remember. It's more useful than they're making it sound, I promise you, if you go on and study further mathematics. But I guess this is just an introduction to the Cauchy-Schwarz inequality. All right. And then you have your additional exercises. Again, some of these are assigned, some are not. I would still recommend looking at all of them. All right, just for more exposure to the material, more practice. You also have the solutions you can look at, but please, try to wait until you're done working on them, till then look at the solution and see if you did okay. All right, don't look at the solutions straight away. Don't just copy them. Right, you're not going to learn anything that way. And hopefully this video was a reasonable guide through this section. If you have any questions at all, of course, send me a message. Send me an email, a Canvas message, whatever, and I'll get back to you as soon as possible. And thank you very much for watching.